the sum and difference formulas for sine and cosine. Our objective for this video: use the sum and difference formulas for sine and cosine to evaluate and simplify trigonometric expressions. So let's remind ourselves what we know that will be useful here. Well, we know the polar or the trigonometric form of the product of two complex numbers. R sub 1 times the sum of cosine alpha plus j sine alpha, so that is the first complex number, times r sub 2 of the r sub 2 times the cosine of beta plus j times the sine of beta. So this is the product of our two complex numbers, is equal to r sub 1 times r sub 2 times the cosine of alpha plus beta plus j times the sine of alpha plus beta. We're going to use this to come up with the sum formula, so to derive the sum formula. And we know the sine of theta is equal to opposite over hypotenuse. The cosine of theta is equal to adjacent over hypotenuse. And finally, we're going to bring in the unit circle values. And I have my unit circle chart here. And I can get most of it on the screen, I think. But we just want to recognize that when we're talking about pi over 6, pi over 4, etc., as we go around, that the x value is the cosine value and the y value is the sine value. Okay, so if we're talking about the cosine of pi over 3, it would be 1/2, for example. So we'll be referring to the unit circle chart and those sine and cosine values as we work today. Okay, so let's use that polar form of the product of two complex numbers to directly derive the sum formulas for the sine and cosine. So I'm going to write this right here. I'm going to write this part first. So I have r sub 1 times r sub 2 times the cosine of alpha plus beta plus j times the sine of alpha plus beta. And I'm going to remember, this is multiplication. This times this times this times this. Thanks to the commutative property, I can multiply in any order I want. So I'm going to combine these two first, and then I'll multiply the next two pieces second. So it's equal to r sub 1 times r sub 2 times the cosine of alpha plus j sine of alpha times the cosine of beta plus j times the sine of beta. Okay, so simply wrote this first, and then I just combined the r's and multiplied them first, and I got to here. Now let's notice that they both have a factor of r sub 1 times r sub 2, so we can divide that out. Those are real numbers, so we can divide those. They're not equal to 0. And then over here, I'm going to do a little, I'm going to do some distribution. So I have on the left side the cosine of alpha plus beta plus j times the sine of alpha plus beta. Okay, if I can make a plus sign, that would help. And I'm going to distribute. So this times this, this times this, this times this, and this times this. So I have the cosine of alpha times the cosine of beta plus j times the cosine of alpha sine of beta. So this times this, this times this. Now multiply these two, plus j times the sine of alpha cosine of beta, plus, well, this is going to be, this one times this one is going to be j squared sine squared beta. Okay, sine squared, whoops. Excuse me, I made a mistake there. Let me go back and correct that. And I got to make it a little bit smaller here. J squared times sine alpha sine beta. Sorry about that. Made a little mistake there. Okay, so first times first, outers, inners, and last, if you like the FOIL method. Okay, now, let's see here. We recognize that j squared is equal to -1. Okay, that is our imaginary unit. So I have here the cosine of alpha times the cosine of beta. And I'm going to bring this and write this next as a minus sine alpha times sine, whoops, times the sine of beta. Okay, plus, I'm going to combine these two terms here. And this is j times the sine alpha cosine beta plus cosine alpha sine beta. Okay, so again, let's remind ourselves this is the cosine of alpha plus beta plus j times the sine of alpha plus beta. So I have cosine alpha cosine beta. J squared is -1, so I subtracted, and then I put my two j terms together and I factored the j out. Now let's take a look. This is the real part, and this is the real part. This is the imaginary part, and this is the imaginary part. So we can set real equal to real and imaginary equal to imaginary. So the real part equals the real part, which means that the cosine of alpha plus beta is equal to the cosine alpha cosine beta minus sine alpha sine beta. Okay? And the imaginary must equal the imaginary. So let's see here. We have the imaginary equal to the imaginary, which means this part, the sine of alpha plus beta, must equal the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. Cosine of alpha times the sine of beta. And there you have it. We just derived the sum formulas for cosine and sine. Cosine of alpha plus beta is cosine alpha times cosine beta minus the sine of alpha times the sine of beta. The sine of alpha plus beta is equal to the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. Now, I derived the sum formulas. I'm not going to derive the difference formulas, but I'll let you know this is how it works. I just let alpha minus beta be the same as alpha plus negative beta, and then I just go through this process again to get the difference formulas. Okay, so basically we rewrite subtraction as addition, and then we'll just use the exact same process to derive the difference formulas. All right, let's take a look. I'm going to recap that at the top of this next sheet here, then we're going to put it into use. All right, let's recap that. So the sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. The sine of alpha minus beta is sine alpha cosine beta minus cosine alpha sine beta. So the positive or negative here, if you go with the positive on the top, if you go with the top here, you go with the top here. So the sine of the sum is equal to these two products with a plus inside. The difference in the sine function is equal to the difference of these two products. With the cosine, it's reversed. The cosine of alpha plus beta, again, the top, okay, so we go across the top here. We're going to go across the top here. It's the cosine of alpha times the cosine of beta minus the sine of alpha times sine of beta. And again, if you go down to get cosine of alpha minus beta, you would go down on this one to get cosine alpha cosine beta plus sine alpha sine beta. Okay? So a couple of formulas that we're going to make use of here, along with our unit circle. I'll leave the formulas there. Let's take a look. Given that the sine of alpha is 5/13 and that alpha is in the first quadrant, and the sine of beta is -3/5 for beta in the third quadrant, find the cosine of alpha plus beta. Let's draw it. Okay, so here are my axes. Alpha is in quadrant 1, and remember the sine is the opposite over the adjacent. Okay, so here's my sine, and this right here is alpha. Okay, and this is opposite is going to be 5. Adjacent is going to be sine is opposite over hypotenuse. My apologies. I bet you were thinking, what is he talking about? I apologize. Sine is opposite over hypotenuse. You would think I would remember that. And so this is the hypotenuse here. This is the right triangle. And this is 13. Okay, well, we'll use the Pythagorean theorem in this right triangle. And we'll recognize that this is going to be 13 squared, minus 5 squared, the square root of all of that. So this distance here on the x-axis is equal to 12. This is a 5, 12, 13 right triangle. So here's alpha in quadrant 1. The sine of alpha is 5/13. If we use the Pythagorean theorem, this length along the x-axis is 12. Let's do the same thing for the sine of beta, which is in the third quadrant. Okay, I'm going to go around to quadrant number 3. I don't need to be too fancy. I just need to have another vector coming into quadrant number 3. And there it is. I'll draw my right triangle to the x-axis. Okay, and so beta goes all the way around to here. However, we also know that when we do the sines, that this is beta here as well. Beta is this angle right here. Sine again is opposite, and this time I'll get it right, opposite over hypotenuse. Okay, well the vector always has a positive magnitude, so the opposite, this would be -3, opposite of beta. The hypotenuse would be 5. And if we do the Pythagorean theorem again, okay, we come up with this being -4. Okay, -4 because we're in quadrant number 3. And in quadrant number 3, the y value is negative and the x value is negative. -3 squared plus -4 squared is equal to 5 squared, 25. So now I have my angles set up. And let's remember, find cosine of alpha plus beta. The cosine of alpha plus beta, well, heck, it's right up here, is equal to the cosine of alpha times the cosine of beta minus, because I went across the top here in this kind of doubled up formula, I'll go across the top here, minus the sine of alpha times the sine of beta. Well, the cosine of alpha, here's alpha. Cosine is adjacent over hypotenuse, 12/13. Cosine of beta, here's beta. Cosine is adjacent over hypotenuse, -4/5. minus the sine of alpha, we were given that, 5/13. Or we could again look over here, sine of beta, again we were given that, -3/5. Let's do the multiplication here. This is going to be -48/65. This will be a positive. Looks like it's going to be 15/65. And the answer comes out to be -33/65 as a fraction. Okay, so the sum of cosine of the sum of alpha plus beta is -33/65. Okay, let's continue. One of the things you can do with these formulas and your unit circle angles is you can find the exact value for angles that are not angles we're familiar with. For example, the cosine of 15 degrees. We want the exact value. And we want to use this the same as the cosine of 45 degrees minus 30 degrees. We know these angles. And we can use this difference to find here using the difference formula. So let's see here. We're told the cosine of 15 degrees is the exact same thing as the cosine of 45 degrees minus 30 degrees. This is the cosine of alpha minus beta. Okay, well, from up here, cosine of alpha minus beta is cosine cosine plus sine sine. Okay, so go back to here, and we'll say this is the cosine of alpha, cosine of beta, plus, remember the cosine function, if this is minus, this is plus, the sine of alpha, which is 45 degrees, times the sine of, the sine of beta, which is 30 degrees. Okay, now let's use our unit circle. Cosine of 45 degrees. Let me get the unit circle out, not that piece of paper. Okay, so the cosine of 45 degrees, here's 45 degrees. The cosine is the x value. It is √2/2. If I got that in there for you, let's pull it down a little bit so make sure you get it in there. Cosine of 45 is √2/2. So this is √2/2 times the cosine of 30 degrees. Let's go back to here. Get my unit circle chart in there. Here's 30 degrees. The cosine is the x value. It's √3/2. So times √3/2 plus the sine of 45 degrees. Okay, go back to my unit circle knowledge. Here's 45 degrees. The sine is the y value, which is √2/2. Times the sine of 30 degrees. Okay, go back to my unit circle chart. Okay, I know 30 degrees. Here's 30 degrees. The sine is the y value. It's 1/2. So times 1/2. Now there's just a matter of doing some math. This first one is the square root of 6/4. This second one is the square root of 2/4. And the exact value is the square root of 6 plus the square root of 2/4, which is a common denominator. So it's one way we don't have an exact value for the cosine of 15 degrees, but we can use the cosine of a difference between two angles we do know to come up with the exact value. Okay, let's continue. Give me a second, my papers are sticking together. There we go. I got two more examples for you. Straighten this up. Let's get rid of this one. My notes. Okay, simplify the expression. The sine of 3x times the cosine of x minus the sine of x times the cosine of 3x. Well, let's remember, we know this is like an alpha, beta. So we know that the sine of alpha times the cosine of beta. Whoops, excuse me for a second. We know the sine of alpha times the cosine of beta minus. So this one got a little bit. This one gets a little bit funky because we can write the cosine. Let's do that so we can see it a bit more clearly. Sorry about that. I just noticed something on my paper and I want to make sure we can see this more clearly. Okay, we're not really used to what it looks like here, but we can say the sine of 3x times the cosine of x, and I can simply write this. I'm multiplying, so I can write it in any order I want. So I'll do it as the cosine of 3x times the sine of x. So now it should look familiar. Okay, now we say, okay, we switch this and we have a familiar look to us that says the sine of alpha times the cosine of beta minus the cosine of alpha times the sine of beta is equal to the sine of alpha minus beta. So we took our sine of alpha minus beta, we wrote this formula kind of in the backwards direction, and we see that it matches up. Alpha is 3x, beta is x, alpha 3x, beta x, and we can say, well, hang on a second. That means the sine of 3x times the cosine of x minus the cosine of 3x times the sine of x is equal to the sine of 3x minus x. That was pretty simple. 3x minus x, of course, is just 2x. And so we have simplified this expression. Sine 3x cosine x minus sine x cosine 3x is the sine of 2x. Be aware, you can multiply it in any order you want, so we can make that change there if necessary. Okay, let's do one more that looked kind of similar, maybe more of an application problem. In analyzing the motion of an object oscillating up and down at the end of a spring, so we're bouncing up and down, the expression sine of Wt plus alpha cosine alpha minus cosine Wt plus alpha times sine of alpha occurs. Okay? Simplify. Well, let's think for a second. This looks awfully a lot like the sine of alpha times the cosine of beta minus the cosine of alpha times the sine of beta. If we let this be alpha and this alpha can be beta, that's all right. We can see how that matches up. And we know this is a difference formula. Sine alpha cosine beta equals, minus cosine alpha sine beta. Well, that's equal to the sine of alpha minus beta. So, let's do this one. The sine of alpha, which is omega t plus alpha, times the cosine of beta, which is alpha, in this case, minus the cosine of alpha, which is omega t plus alpha, times the sine of beta, which in this case is alpha, is equal to the sine of alpha minus beta. Omega t plus alpha minus beta, which is alpha. Well, that's not too bad. Alpha minus alpha is 0. So this simply becomes the sine of omega times t. And so that one is simplified. So there you have it. A fair amount of work with the sum and difference formulas for sine and cosine. Next up, the sum and difference formulas for tangent.